Hi, I'm Johannes Bechberger, and I'll be telling you all about building a lightning-fast firewall in Java, because why not? And I'll show you in a minute why. But consider we have a simple web application. Maybe some of you also run simple or slightly more complex web applications. And for example, for me, it's my JFI events website, so I'm doing Java profiling stuff at work, and so I create a small website. And consider now I have a DDoS attack, and that means someone calls it a gazillion times, and what do? The naive way is I could just cut the Ethernet cable, for example, with my lovely Viking axe, or I could just cut the Ethernet cable of the attacker. That would probably also be usable. But in reality, I probably just drop the packets in my application somehow. That would be the easiest way. For example, here you see that I just consider this as a server application. Every time a package comes in, I check the address against a set of block IP addresses, and I then have a simple method that's like, oh, should I block this IP address? And then it just return, and then it just close the connection, and that's fine. But there's a problem. Can anyone spot it when we get DDoS? When we get DDoS, why this isn't a good idea? Anyone? The main problem is here that it happens quite late. So if you have our network stack here, we have on the lowest layer we have our network interface. That's actually where like we put in the Ethernet cable. Then we have the whole Linux networking stack. Then we have our application. So essentially, what we would be doing when we're doing it on application level, the package would have to drive all the way through the network interface back up, and then this would cost us quite some performance. So we could, of course, use a firewall. That's like the traditional approach to reduce, to remove the connections that a malicious attacker opens to us. So here in this example, I just use a call to IP tables. This removes this IP address, and so it's blocked. But how can we improve it? Because if you see here, that's pretty fast. So that's already pretty fast. You see here the application it. In experiments the Cloudflare did, the dropping it at application level, you can drop like around 200,000 packages per second. But it's when we go to IP tables, we get into a range of 1.8 million. But we want to become a 10x developer, or 10x firewall. So what do? We look into other possibilities, and one possibility is to use XDP, the Express Data Path. And you see here that we can almost block 10 times as much. We can block as many packages as essentially come in over the over our Ethernet connection, because it's fairly close to like the 10 gigabits if you assume that like an IP package has like kilobyte size. So that's pretty cool. And how does it work? It works because XTP sits between the network interface and the Linux networking stack. So it's essentially the first point where we properly have the package in the kernel, and there we check it. And what's important is that allocations of packages are really, really expensive. So a package is first allocated whenever it comes over the Ethernet, because we have to somehow write it down, we have to somehow record it. And then it's the next time allocated when it enters into the Linux networking stack. And then in the end, of course, it's also again allocated when we obtain it in our application. And the cool thing is with this, this technology even allows us that we can offload it from our CPU, because as you see here, we're so close to the network interface. Some of the more modern networking interfaces even allow us to do all the things I show you in the following directly on device, which is pretty nice. So XCP is part of the Linux kernel, kind of, and all these things close to the network interface are part of this. And so how can we modify it? Because we want to essentially modify it so that it drops packages from specific IP addresses. There are two ways. And the first way is to change the kernel. Essentially, we directly hack into a kernel and fix it, and then hope that Linus Torvalds accepts it. And that is highly likely, as everyone knows, especially when you're a newbie kernel developer. And then we can, of course, also create a kernel module, which would also be possible. But the problem is, it's really hard to write these, especially because the API isn't stable. To quote one of the kernel main developers, Craig Hartman, you think you want a stable kernel interface, but you really do not, and you don't even know why. The thing why we don't have a stable kernel interface is just because the kernel isn't optimized to having a stable interface to like internal kernel modules, but to the outside, of course, because when you do application development, you want to have a stable interface. But the main difference is here that inside the kernel, we want to have speed, we want to have security, and much more. So if you write a kernel module, you're essentially at the mercy of the kernel developers. They can change something and then it breaks. So only write kernel modules if you have the manpower to maintain them over time. So that's not really a good option. So can we do better? And that's where my talk comes in. Of course we can do better. So in around 2014, people decided that, hey, we have software-defined computation, also known as like containers. So with Docker and other tools in Kubernetes, we can essentially describe how our compute landscape looks like. Oh, we have this part here, this part there, they communicate and fine. But what we didn't have any software-defined networking. We couldn't describe anything that happens on like the network layer properly, and also extend not only the compute definitions, but also extend the whole composability and else to the networking area. And so this is where eBPF came in, and then later extended, as you see in a minute, to many more spaces. And so what is eBPF? eBPF is a crazy technology. It's like putting JavaScript into a Linux kernel. This is a quote by Brendan Gregg, who popularized it in like the late 2010s. That's him shouting at hard drives because I don't know if you know, but when you had these old spinning disks, all the people here in the room know them still. When they vibrated, and vibrating can be caused by just shouting at them, they have different latency characteristics, so they have to slow down a bit, and that's what he tried out, and it worked. And so if you want to see a Chrome man shouting at hard drives and being really happy, I have the YouTube link down there. Anyway, just search for Brendan Gregg. It's probably his most viewed video. He's essentially known for this. Anyway, he's also doing lots of great things in the profiling world. He, for example, invented Flamecraft, if you ever heard of them. And that's him when he's not shouting at hard drives. But back to the topic, as he said, eBPF allows us to make the Linux kernel programmable at native speed. It's essentially like, as Brendan said, like putting JavaScript into a Linux kernel. You can extend many things. For example, you can extend the network layer. And how does it work? It's pretty simple. You have your source code, of course. You write it in a language like C. Then you compile it down to some kind of bytecode. The bytecode is just a description of a simple machine. It has like an add instruction and a push instruction and a call me function instruction. And what we then do, because all this, as you might guess by now, has to run in the Linux kernel, because the network handling it's deep down in the stack, and all the things that we do with eBPF essentially run in the Linux kernel with kernel privileges. So we have to push them somehow in there, and that's where the BPF syscall comes in. We can tell it like, hey, here's a program that I wrote, please load in the Linux kernel. Of course, you need root privileges. And please don't run random eBPF code from the internet. I show you later in a demo that you can do pretty nasty things with it and have lots of fun. You can even write code that is not deletable because you can mess with the file system, which is pretty cool. Anyway, so what we then have, we load it in, and the problem is if you ever program Java, you know that null pointer exceptions happen quite a lot. And if you ever wrote C++, then you probably also know that like segmentation faults happen a lot, and you don't want to have segmentation faults or null pointer exception in the Linux kernel, because then essentially your system becomes unusable and it's really hard to backtrack. And so what the verifier essentially does, it checks your program. It checks for for the non-existence, it checks that things like segmentation faults can't occur. Essentially, every pointer you access, the verifier must make sure, oh yeah, that's a valid pointer, that's not a null pointer. And it also forces termination, because we want to know that the program that you load in, that you attach to a hook, like a networking hook, actually terminates sometime. Otherwise, your kernel would be pretty stuck. Of course, this is a problem, as anyone who listened to some computer science classes in uni knows. That's not always possible, because when programs are true and complete, we can't guarantee that they terminate, or we can't analyze this behavior. So essentially what we do here with eBPF, we have a limited amount of instructions that we can execute. So the programs usually written with this eBPF are not that large, but large enough to have some fun. What we then do, we put it into a JIT compiler usually, because it should be fast, because when we, like you say before, when we have packages coming in at megabytes per second, gigabytes per second in our system, we don't want to wait too long for it. And so it's JIT compiled usually on all the major platforms like S390, Z, and PowerPC, and of course also on the lesser known platforms like x86 here. And so what we then do, we have these large programs, we have these small programs, and we attach them to hooks. It's more like when you're doing, for example, a React program, when you're doing front-end programming, where you say, oh, whenever someone clicks on something, I want to execute this, and that's essentially what we do here. We can go into a network interface whenever a package comes in, call my hook, and then do something about it. We can do the same things with sockets. We can do also for any system call. We can also hook on and be like, oh, whenever the system call is called, then do something. And that's also how we get information from the application process, because essentially application process usually interact with syscalls, and so we can also monitor our application. And so what does eBPF give us? It gives us safety and security, because we have a verifier that checks basic things about our programs. We can do continuous delivery, because essentially we can modify the kernel at runtime. We don't have to recompile the kernel every time. That's especially important when you want to test your things. And it's pretty efficient, and it's a standard. So the eBPF runtime, it's standardized. We have in a way relatively stable interfaces, so we can write our programs and be sure that they probably run in the next Linux kernel too. And that's pretty nice, and it allows us to do this also in small teams. So this is technology that many of the new security vendors use, because it's pretty cool. So of course, I showed you that we can like attach things there, but we also need to exchange data, because a program where we only like run it and then it does something and doesn't like communicate with the rest of our system is probably pretty dumb, because, for example, we can't update our IP list that we want to block. So the two traditional ways to share data in our programs would be, one would be via socket. So essentially program A sends program B a message. The other one would be via shared memory, so both access the same area of memory, but both aren't really suitable here, because sending messages is pretty high overhead, and to implement things like hash maps that we share between both, this would be pretty hard and not really computationally efficient. And shared memory is also not a good idea, because essentially we would be accessing kernel memory, and yeah, we shouldn't do this from our userland application. So what do we do in the end? We use something called eBPF maps, and these are essentially data structures that the kernel gives us and that we can access using the BPF system call, both from like the userland and from the kernel land, and use this to transfer data. And so how it works essentially is that our eBPF programs, our small snippets, they access the maps, load, for example, the IP addresses that should check for IP addresses that should be dropped, and also we can get the data out to our userland application. And it's for anyone who developed C before, and in C you don't have usually like a hash map or such. That's not great. But here in eBPF land we have things like arrays, even hash maps with least recently used semantics. So we have essentially caches, we have ring buffers and more, and even like things like priority queues, which makes it really a really capable tool. And we can hook, so I told you before, it's essentially everywhere in the kernel where we want. So there are countless hooks. We can go into a file system. We can go in every system call. Everything about storage, we can even use like Linux security modules to develop our own security applications and more. And one of the big uses is also tracing and profiling, so we can get a lot of insights into applications. And this is language agnostic, so we see everything on the system, and that makes it really powerful for this. And as I said, you can use it for security control. And that's especially important because I don't know whether you noticed there was some kind of bug in the news last year. And this is from an airport. I think it was in Zurich or such. And there was CrowdStrike. Essentially, the main issue there were this, that this company was developing their own kernel modules for Windows, and they had a simple bug in there that the eBPF verifier would have catched, and then everything drew to a halt. This wasn't that great, but with eBPF that could have been prevented because eBPF has the verifier. This would have prevented the bug, and with eBPF it's far easier to reload something, to patch something and push it out than with this. And since then, the people at Microsoft are also thinking about using eBPF, and there's more and more thoughts of getting eBPF out of like the Linux niche onto the broader operating system market to also support Windows. But of course, eBPF has bugs too, and some of them even with high CVE ratings. The main thing is here that most of the bugs occur in the verifier. And so, yes, this is a problem, but if I'm honest, you should only run eBPF code from trusted sources anyway. Please don't download them, I don't know, from your random GitHub gist and run them on your production machine. That's not great. And even if you run them on your, even if you write them your own, please also don't run it on your production machines. It's really easy to mess it up, and please test them, because eBPF has so much power and so much capabilities. Now here to the eBPF ecosystem, you see here that in the lowest level we have the kernel runtime that runs in the Linux kernel. And so we have the verifier, we have the maps, we have the helper API, and then if we go a little bit higher, we have like in user space our SDKs. We have SDKs, as you see, for C++, Rust, and other languages. And I think in the security space, Go is pretty big, so there are also like SDKs with which you can write eBPF programs in Go. And then above are programs that are really helpful, for example, Katra and Pixie, a tool called Falco, and many other tools which you can use to do, for example, load balancing and also security applications. If I stand correct, then Falco is something that you can use to like do set security guidelines for your system, and that's pretty helpful. But you have to be worried that like they use a lot of eBPF stuff, and sometimes a small change in the kernel can cause interesting bugs in Falco. A colleague of mine had an issue with like, oh, it didn't work, and so what it was is that in one kernel minor version, the verifier got updated and it dropped more programs, it disallowed more programs, and then Falco didn't work, so he had to update Falco because, yeah, it's stable, but it's still an early technology, so I wouldn't assume that everything works there. But of course, there's one language missing there. Anyone has a guess which language is missing there? Anyone? Yes, Java, and it's there because like a year ago I thought like with Brandon Greg, eBPF is a crazy technology. It's like putting Java into the Linux kernel. And to quote a famous trailer for the JavaZone conference, which was here like half a year ago in Oslo, I want to use a programming language which doesn't only run on userland. So I want to use Java there, and maybe that's not the point in the presentation where I can tell you who I am. I'm a Java developer, so I work on Java itself. I'm not a Java user. I work on the JVM at a little-known company called SAP, where I'm at Submachine. You can see the logo here, I have stickers, and we're like the third biggest contributor to the OpenJK, and working on Java, adding things like null pointers and else. And a year ago, I started developing eBPF applications in Java because I can. And that's the result is Hello eBPF. It's the first and currently only, for good reasons, Java library for eBPF, which allows you to write, for example, firewalls in pure Java. Because why not? And it's fun, and in a minute I show you a demo. And of course it's work in progress. Don't use it in production. Use it for you can use it for education and having fun. That's where I use it for, and for testing. But yeah, now we come to the interesting part of the presentation, and that's called live coding. Because I think we've all been here at the conference seeing talks where the presenter just stands. Sometimes the presenter also wants to sit. So I hope you can still see me. It's the chair is a little bit lower than I expected. Anyway, let's see whether it works. So on live coding, or as I call it, having fun with eBPF, and yeah, and the verifier. Anyway, here for the name giving demo, it's the firewall demo, and if everything works well, we can go to our demo. So essentially what I did here, I created a simple firewall that has a Spring Boot-based front end. In the front end, it's like written with some JavaScript that ChatGPT generated me because I'm not a front-end developer. But essentially what it does, it pushes the data almost directly into the kernel. So what we can do here, we can trigger a request, for example, to check whether Google is reachable. So you see here, it's probably reachable. I can even show you that is Google reachable? Probably, yay, it's reachable, yes. But now what we can do, it's a firewall, so let's add some rules. For example, here the rule is take every IP address and that every package that comes in on port 443, that's the HTTPS port, and just drop it. So that's what we can do. And now we trigger the request again, and it's blocked because that runs essentially directly as close as possible to bare metal as we can, as close as possible to like the Ethernet cable or like the Wi-Fi signal coming in here as possible. So this blocks it and is really fast in this regard. And this is all written in Java, which is pretty cool and slightly frightening. Anyway, so how this essentially works is that you see here that we can packet in from the whole internet, and what we do, the packet comes into a network driver, is parsed because we're doing like the Wi-Fi stuff where we pass the packages and things. But essentially our raw Ethernet package comes in, and then what we do, and then what it does after it's like basically parsed, the Linux kernel asks our eBPF program that we registers, hey, is this okay? What should I do with this packet? And we then analyze it and be either like, yeah, that's fine, let it through, or we're like, no, please drop it. And the other thing what we can also do is, of course, we can log. So we can say, yeah, pass it through, but I stored some sneaky information. And my end goal is to write a blogging platform that runs entirely in the network stack. That would be pretty cool. Screw WordPress, I'm going native kernel. The only problem is that I then realized how hard it is to implement my own TCP/IP stack. and my own HTTP stack in a language in eBPF, which has a limited amount of instructions that I can execute. So it's probably something for later sometime. Anyway, then the package goes through the network stack. It goes into application. If we're fine, we can access it. But what our eBPF program then does is it can communicate. You saw here that we submitted a package. We submitted a rule. We push it down into a map. We store it and then get it up. And the cool thing is when we look at the code, and when we look at the code, oh cool, yeah, you see here I log a lot of things, so I just quit it so we don't log all the time. When you look at the code here, and we have these are like the if any one of you developed some Spring Boot. That's essentially where we come in. So when we add a firewall, what we do, we parse it somehow, and then we add a rule. And the nice thing is that's our BPF map. That when we call put, we directly put it into the Linux kernel. We don't do any checking. So be aware that exposing your firewall to the internet is not a good idea. Please don't do this at home. This is slightly frightening, and that's one of the reasons why everything I have here is local, and my presentation doesn't run on Google Docs online, because otherwise the presentation would be over till now. So anyway, I wonder how I would do this presentation when it would be online. It would be pretty funny. Anyway, so this pushes directly in, and how our firewall works, it's essentially a small class we can define. The cool thing is we define some types like a IP and port as a record. We define firewall rules and can use them both in Java and in eBPF. And so what our main application does is we just load our firewall and then we do some things. But that's a bit complicated, so let us start with a simple example. So what we can do with BPF, with my library, we just say, oh yeah, please, this program should be a BPF program. This program should be a BPF program. And of course, yeah, we want to extend, for example, our BPF program. And we want to do something simple. I showed you before that we can use system hooks, and I disable GitHub Copilot for now. I feel it's not worthy. So we can just implement the interface system call, and then we see quite a few methods here. For example, we get all the methods like for many of the system calls, like the system call dub, like the system call eport create, whatever. I'm not too deep into this, but what we can do, for example, every time a normal application opens a file, it uses openmet2 for whatever reason. But what we can do, we can print it so that every time someone opens a file, let's print it, and there's some helper methods here which we can use. BPF print trace bin k, so we can just say hi file and then be fine, and just pass it the file name. And the cool thing is now when we then attach it later, we see every file that any process accesses. And so what do we do here? We now have to, of course, somehow load it. So how it works is that the buff code runs in the Linux kernel, but now we are in userland again. And so what we do, we have our program, we load our program. BPF program load. There's lots of magic happening behind, so that it kind of works. And then that's how we loaded it. And of course, we have to attach it, so we can just call it auto attach, and then we just tell, hey, please give us a trace print loop. So essentially, we print here to a trace, and this is how it prints. So then I always have to make sure that I'm using the correct Java version, because it needs modern Java, not like your Java 8 or something. So then we build it, And this can take a while because it essentially compiles this down partially to C, as I'll show you in a minute. This is compiled down to C, loaded into the Linux kernel, and this runs on the ones here. And I have a bug. That's nice. Let's see what it had problems with. And I don't know what problems it had with. Let's do a Maven clean. I'm not an application developer, so did it break? Looks at least better. So this is all like the whole compilation process is integrated into Maven and things. And that looks nice. So I think I can just ignore it. Fingers crossed. Oh, I think I can just. I hope that I can just ignore it. Anyway, let's hope that I can just ignore it. You see, one of the problems is that eBPF likes to have things in its order. So let me check shortly what was wrong here. Oh yeah, the problem is eBPF and divisions is like a minefield. This worked a couple of. This worked a while ago. Good old eBPF. So a problem, of course, is that it just told me that it has problems. Wish me luck. It's really limited in what it can do. Essentially, the main problem with eBPF is that it's so restricted because the idea that the developers had was make this runtime as tiny as possible so we can port it to any system, to any modern architecture that anyone would use, so we can write and JIT quite easily. And that's why they only have 7 registers and such. So it's good enough. Let's hope that it now works, else I use the prepared things. Good, it worked. Now we can just run it. Demo.sample. Cool. And now you see a problem that you usually have and that I didn't have at doing this before, that we have a verify issue. That's real nice. What it tells you, and I totally forgot, is that you see it here, and that's a good thing they told us, is cannot call GPL restricted function from non-GPL compatible programs, because we need to tell in our program, say, yeah, we're GPL licensed. The thing is that if you know the GPL, you know that when we write a program and we call GPL licensed functions, our code itself should be GPL licensed too. Some of the methods are exempt, but most of them aren't. So let's do the whole thing again. The cool thing is we have now live debugging on stage. That's what I like. But the cool thing is, before, when we were in the olden days of like normal Linux kernel development, we would have to recompile our Linux kernel, and that would take so much longer, and just say, oh yeah, load it. And my system doesn't break. So you see, we just had an error. The verifier catched it, that it likes licenses a lot. Good. Now we see here that these are all the files that are accessed, and that's pretty cool. That's like only a few lines, and we can do logging. We could use this, for example, to do monitoring, to see, are any files accessed? Are there any malicious patterns of file accesses here? And this is used by tools like Falco to do monitoring here, just because it's so easy and it's so fast. It doesn't impact the application a lot. The cool thing is with this, we can should we do something more illicit? Anyone? So what we can do, we can forbid a file. So guess we want to forbid that people can touch tmb/forbidden. I think there should, no, we create a file. We want to restrict people from accessing this file. How can we do it? What we know here is that all the programs usually go through enter-met to access these files. So what we can essentially do it, we can modify it. We can read the file name because the file name is from user land. Memory is something that's quite interesting in eBPF land because it's not, you can't directly access user or kernel memory, but there are methods for it. So essentially we copy the file name in, and then we check, is it forbidden? We just check with a simple loop, is this the /tmv/forbidden file? And then what we do, we of course trace it. We want to know what we're doing, and then we write into the file name because it's a jar pointer. So it's a pointer we can write in. So we are sneaky. So essentially, what we do, we write in an empty string. So what happens when you load this? That's pretty simple. Forbidden file. It's real simple. So what we can do here, we see here every file that's loaded, but when we now access it, ta-da, it doesn't work because when we enter it, so that's the first thing that Linux does when the system call is called openmet2, and then we modify the file name. So what essentially happens is that the later code in the system call is then like, I don't know any empty file. Please, what are you doing? And that's a simple way to prevent the access. Of course, when we have things like symbolic links, we can circumvent this. Another cool thing here is, and we're going closer to the firewall trajectory, we can, for example, write a simple program that drops every third package. That's useful for stress testing our application. It's useful for checking, yeah, our package behaves when we have like adverse networking condition. So we implement again interface, this time called XDP hook. That's like before. It has one method that's called XDP handle packet. That's called when, as I showed you before in the graphics, when the system needs to decide what to do with this package. So we then set a counter, and we have a simple method should drop, which essentially checks, is this counter model 3 equals 1? If yes, we drop it. If no, we pass it. And that's pretty simple. That's a simple way to implement a firewall, kind of a firewall because it only drops every third packet, but you can assume that you can do here much more because XDP, because our context contains the whole packet, we can parse it and do some proper parsing. The only issue is that, of course, at this point, we don't have any IP addresses stated in. It's only an Ethernet packet, so we have to implement our whole network packet parsing ourselves. And it's quite a lot of fun, I can tell you, especially because it was like 10 years since I had this at uni. But that's like a thing with eBPF that you have to do many things yourself if you want to be fast. And this essentially drops us every third packet. But what I can also show you is how this whole thing is implemented. So what we have here, we have our code. Here it's the global variable that we can access both from user land and from kernel land. And what we do now, I first pre-process it so that we remove all the, I state all the global variables, all the types in C code. And what I do, I get this Java code, and what I essentially use is a translator that translates me the should drop method in Java to equivalent C code, and then in the end we get this, and this is how the whole library works. Because of course C is like the most used language for these eBPF programs, and also Rust is now gaining popularity. Java is just because I can. Don't ask me why. I once gave a similar talk at the Linux Plumbers conference in September, and people thought it was a joke when someone else told them, yeah, you can do eBPF in Java, and they were like, what? But that's fine. It's just a simple project, and I'm happy that you're here and not laughing at me all the time, because you probably some of you probably program in Go, and I programmed it for the last 2 days, and I have to say, Java is an interesting language, but Go. For example, I tried to get a list of keys of a map, and it's a for loop. Anyway, every language has its pros and cons, and here what I try to do is I try to show you what cool things eBPF can. And for the compile notes here is short job is translated into the simple bytecode by LVM. It's pretty simple. It loads like our global variable. It adds something on it, and then it has a simple jump in because, of course, like the ternary statement is because, of course, it's like the ternary statement is essentially an if-else statement, and that's pretty simple. So now to the end of my presentation. What I want to do is that I want Java as a first-class language for eBPF because I think it's cool that we can write these programs in Go and Rust, but it's also cool that we can now write them in Java because many of the, especially junior developers and people from university, mostly know Java, at least in Germany where I come from, so it helps them to understand what we're doing. And it helps us to go, eBPF as a whole helps us to go towards a microkernel because before we had to implement our firewall like close to the Linux kernel, and now we can just implement it externally loaded in, and that's pretty cool. And of course, when we have kernel fixes, we can, for example, patch the kernel from the outside at runtime. For example, consider we would have an issue where like a file name was terrible and it crashed the kernel internally or our file system. What we could do now, we could just add a fix and be like, oh, whenever this file name comes in, we just drop it. So it's a simple fix, and we can really use it for hotfix. And then a topic that I'm particularly interested in the last few months is it's SCADX. That's the official logo. What it does, it essentially allows us to write our own Linux kernel, our own Linux scheduler in Java, in eBPF, and thereby, of course, in Java, because I implemented this. Why not implement a Linux scheduler in like 10 lines and run it alongside a presentation in front of you? Because, as you might have guessed it, the whole presentation ran on a Linux scheduler. It was essentially the scheduler where there was a tiny bug in that. But that's the Linux scheduler that's running this whole system, this whole presentation. It's just like 10 lines. So what it does, it initializes a scheduling queue, and every time a process is like, yeah, I wanna go on the CPU, please, scheduler. We just tell it, yeah, go into the shared queue. We have a time size of like 5 milliseconds, and we scale it by the number of waiting processes, so the system is still responsive, which is pretty useful for running a presentation on it. And then every time a CPU is like, hey, please give me something new. It's essentially like a junior developer is like, please, boss, give me a new work item. And we give it here. We just say, yeah, take the first one. We don't care. And that's a fully functional Linux scheduler that works. The overhead is not that big. It's of course not that great. We can implement simple schedulers that are far worse. We can implement ones that are better, and people at Meta and NVIDIA and other companies working day and night on making useful schedulers. And the cool thing is, because we have a few minutes, so I just find it interesting. For example, we can normally our system is normally we want our system to be really responsive. So we want that our system executes a new task every few milliseconds. So yeah, responsiveness is nice. Now consider we just say like, hey, please let processes run for like 5 seconds on end. Let's see where that crashes our system. I hope it's also interesting for you. It's just some nerd stuff that I do. Let's compile it again. Fingers crossed it works this time. And the cool thing is all the eBPF bytecode is integrated into the jar that comes out of this, which makes it also possible to transport this to another system. Let's see. It didn't crash till now in the build process, so yes. So yeah, it worked. So I have to check. So what I do is I kill all Java, so I don't want to have the previous scheduler on. Sorry, one sh minimal scheduler. So now we have a scheduler that I hope it's this scheduler. Yeah, that's the scheduler, and it's okay now because we don't like do something drastic on our system, but consider that we call Maven package. And you see here we can have fun. And we can even get it to a halt because when I start compiling the OpenJDK, because that's like what I do for work, if you ever wondered, I'm one of these weird people that do like profiling stuff directly in the OpenJDK and find for a couple of years to get them in. So let's see, do I have a JDK on? Because the JDK is really good in like heating up your system. Oh, yeah, make clean. That's probably a good idea. And you see here, it's really jumpy, but we can improve this, and it's really funny. So that shows you what we can do with eBPF, having fun. Also, for example, using this to simulate certain conditions. For example, if we want to simulate our system on the load, we can just write a Linux scheduler that simulates, that behaves like it's on the load. And another idea that people came to recently was we could also use this in security applications because we can control how long a process works on stuff and then only run the next system. So maybe we can use this for security too. Let's see. And you see here, it's not the most responsive scheduler. Anyway, I just stop it and go back to my presentation. So yeah, you can writing your own Linux scheduler is as easy as implementing the scheduler interface and hoping the verifier doesn't hate you. Thank you for being here. It's always nice. It's the second time that I gave this talk at an NDC-related conference, and it's always a pleasure. When you want to find out more about all these topics, go to this QR code. I'm Johannes Bechberger. You find me at mostlynodeless.de, where I publish a new blog post every 2 weeks on eBPF and such. There are now over 18 blog posts out on eBPF. For example, there's also a blog post on the whole XTP stuff, on the whole writing a firewall stuff, where it's far more in depth than I could ever go here. There will be next week, hopefully, a blog post out on using custom Linux schedulers for concurrency testing. So if you're at FOSDEM, you can look forward to me being prepared in this talk. And yeah, I want to say thanks to my team. It's really great that I can do such interesting work on the side there. Yeah, and if you have more questions, then I think we have still 10 minutes. But yes, thank you.